you have gone through it. Have you gone through it or not? Is there anyone who has looked at the lectures?
Yes, sir.
Okay. Okay, I think let's not waste any further time. I would like to start the class. It's 1:30, so you have enough break, right? 12:30 to 1:30 is a break, or Abhilash, it's a break time, right? 12:30 to 1:30.
Yes, sir.
You have that habit of coming in time. So lab also you are delaying a lot.
I mean, sir, we were unable to join until 1:30, sir.
Oh,
that's the reason.
Because the time is 1:30, right? That is the reason probably.
I mean, we generally start joining 5 minutes before, sir.
Okay, then we will wait.
No, that's.
So what will happen is that I should have joined earlier. I think if I have joined, then others can easily join, because I being the author, I being the owner, not author. So let's wait for 5 minutes then, and then we will start. So the thing is, like, we are planning to have your minor in the next week or so. Okay, in the next week, Friday, we're actually thinking of. So please be prepared for it. If any changes is there, further changes is there, I'll let you know. We have not communicated to the CRs also. I think Sachin sir has might have talked with the A section students, and I asked him to fix a date after talking to the students. So probably he will. Kalyan, do you have any idea whether he fixed anything? A section students has talked with you?
No, sir. No.
Okay, probably he might have just decided that he might have asked me permission that we will consider it on Friday. So is that is that okay? Friday timetable, Friday minor, not this Friday, next Friday. This Friday is a holiday, so the next Friday we are thinking of having a minor one.
Okay, sir. No problem. Next Friday.
So please schedule that. Okay. Please
yes.
Schedule that. If anyone asks you, please let them. So I'm telling you almost 10 days before. Please be prepared for the minors, and mostly the concepts, fundamental concepts. We will only talk about the concepts only. We will only test you about the concepts only, a little bit critically. So be sure with what you have learned. That if you are sure about that, you will be able to get. You can score very good in that. That's not a problem. Okay. So far, I hope you have got no doubts. Have you tried the problems that I have given in the PPTs? So please have a look at them. If you have any doubts, we can discuss. Otherwise, we can please try to solve them and be ready for them. So 1 mark questions may come through this also. Okay, 1 mark problems may also come in the manner exam. Okay. Right. So it's 50 students now. So I think let's start the class. So here we are dealing with the analysis of experimental data. Okay. So in the previous classes, we have looked at types of error. We have started with different classification of types of errors, and then how do we calculate what is your calibration? We have understood through calibration. What we are trying to do is we are trying to actually find out or negate or normalize the fixed error or bias error or systematic error. We are trying to know the value of this calibration. Through calibration, we are trying to find out the systematic error so that we can find the true value. The second thing is the random errors. How do you deal with the random errors? We have already looked at that from the statistical analysis. So we have talked about mean and standard deviation, and how do these will affect your readings. How do we evaluate that? All that we have studied in the last class. And then we have moved on to the uncertainty analysis, which is nothing but explaining the range of the deviation with the percentage of confidence. So how do we do that if it is a cumulative function, if the variable is a cumulative function, or if it is a product function, how do we solve that and finally find out the uncertainty? Those are the three things that we have studied in the last couple of classes. And today's class, we will try to wind up the session by finding out the regression analysis. Okay, so here what we are trying to do is we are trying to find out how do you fit the curve, okay, for a given data. And once you fit the curve for the given data, how are you so sure that the curve fit is a good approximation of the given data or the provided data? So from what we are trying to do is from the experimental values, we are trying to devise or derive a mathematical expression which actually replicates the data. So that is what the function of the regression. Okay. So, but before going to the regression analysis, we would like to solve this one simple problem was told in the previous class. So we have given here a resistance of different copper wires, and you know the different copper wires resistance are given, and they're asking us to find out the best estimate for the resistance and what is the error with 95% confidence. Okay, so they're asking us to find out what is the best estimate for the resistance for the given data. What can be the best estimate, and with 95% confidence, what is the error that you will get? So first we need to find out the average. Average is the best estimate for the given data. So you have find out the R bar, which is nothing but the average value. And then you have find out the standard deviation of the error. Standard deviation of the error is nothing but your individual value minus the mean value whole square, the summation of individual minus the mean value whole square under divided by the number of readings under the square root. So that is the value. So from that you will be able to find out from using that expression you got out this value. So the error, the standard deviation that you got is 0.0194 kiloohms from this given expression. And later you have the corresponding error estimate based on 95% confidence interval. Okay, they're asking us to find out what is the corresponding error estimate based on 95% confidence interval. So can any one of you tell me what is 95% confidence interval will lead to what kind of standard deviation? What is the value of the standard deviation? Whether it is 1 sigma, 1.5 sigma, 2 sigma, 3
Sir, 1.97 sigma.
Yeah, so therefore it is 1.96 sigma. So that is basically you are calculating as 0.038 kiloohms. Therefore, you know the R value, mean value, and you know the estimate with 95% confidence. So therefore, we will talk about that particular value. Okay, so that is nothing but 1.22 plus or minus 0.038 with 95% confidence. That's how you will talk about the deviation in the given that's how we talk about the uncertainty in the mean value. So most of the out of 100, 95 values will fall between 1.22 plus 0.038, okay, or other is 1.258 or 1.22 minus 0.03. Okay, so that's why those 95 values will be out of your 100. Okay, so this is how we will solve these problems. So now we will move on to finding out the regression analysis. It's a very, very important topic in the measurements. Okay, let me stop my video first. Okay. Let us move on to the regression analysis first. So in a regression analysis is nothing but, what is this analysis, regression analysis? It talks about the presentation of experimental results or experimental data in the form of an algebraic expression relating the effect to cause or causes. So that is what we are trying to do. Okay. So it is the presentation of experimental results. We have got, we try to find out for a given input, what is the output we try to find. So we got a set of inputs and outputs. Okay. And for those values, one set of values we are calling one sample. So for a given sample or for a given set of results, we don't want to plot every time, or we don't want to show it in the form of a replicant data, I mean, in the form of a mathematical values or data. Instead, I want to show the whole data in the form of one particular equation. So what is the value of that particular equation? We have got this data, so can't we give in the form of numbers? Why do we require this fit, first of all? Why this mathematical equation is required? Can any one of you tell me? So you can write always the number of data. In 2 lines, you can write what is there. X is there and Y is there. For a different X values, what is the Y values? You can write. What is the requirement that you need to have in linear fit or some fit? Why do you want to showcase that mathematical data in the form of a mathematical or algebraic expression? A simple question is I'm not asking.
So like sometimes we need to interpret at a different value. So it is good if we know the like how it functions.
Exactly. So whatever the data is, it's not continuous, right? So we have discrete values. One value here, one value here, one value here, one value here. So these are all discrete values for a given this one. We have got y1. What about from here to here? How do we know how it behaves? We don't know, right? So what can be the best fit? Even in your school days, when you're drawing your graphs, you never know how to join these dots. Some people will say that it has to be joining all the points from here to here, here to here, here to here. Likewise, isn't it? Some may say like that. What I'm saying is, earlier in our school days, we used to draw a curve like this, correct? So what we understood is, it should be able to find out all the points. It should be able to join all the points on the curve. But what is the problem here? To define a curve like this, okay, to define a mathematical equation which varies like this, it has a crest and it has a trough, again, it has a crest and it has a trough, and then it almost linear. So finding a line, it will be a 4th order or the cubical order or 5th order, higher order polynomial equation we will get. Okay, how do we come back to that? How do we get that? That is again a qualitative problem. That is again a mathematical issue. So therefore, the easiest thing that we used to do is, what we try to do is, we used to have a simple or easy linear fit. Okay, we try to have a linear fit. That means it is kind of a line which is equidistant from all the points. Okay, so that means the deviation is, what we are trying to do is, that line has to have a limited, very less amount of deviation. This is nothing but xi minus xo. Here, this is the, for a given xi, you got yi, and this yi we got it from the expression. Let us say this linear fit is y equivalent to ax plus b. Okay, right? So if this expression gives, when you put this value xi into this expression, it will give you yi. Okay, so now what is the value of difference? So now from this is y and this is yi. So what is the difference between these two? Whole square. Or from this value, what is the mean value is differing, and from this your yi minus mi. So from this expression also you will get another yi. So that minus its mean value. So when you find out the deviation, it has to be minimum. So that is basically your requirement. Are you getting me? So whatever the line I'm drawing, that line should make sure that the deviations from the line to the points, actual points, should be minimum or 0. That is what our aim will be. So therefore, we will try to join as many points as possible, and we always try to have a linear line because it's easy to draw. Okay, it's easy to define. Okay, and then Sir, is the only linear fit? No, we have so many data. So we also have another data here. This is a linear relation between y and x. We also have a linear relationship with logarithmic y and x. Okay, we also have a polynomial fit here. So if there is the data is varying like this, you cannot define a linear line. If it goes like this, only 3 points are joined. What about these points? So you cannot draw a linear fit for such kind of a data. So therefore, you have to draw a polynomial fit. So whether it is first order, second order, third order, fourth order. So as you go on increasing your order, your complexity of the equation in solving that equation becomes more and more difficult. Anyways, now you need not sit in the earlier days in the mid 70s and 80s when computers were not there, people have to sit and do the mathematical analysis, find out the exact variable values of A, B, C, D, depending on the order of the equation. Those values they have to solve and find out. But thankfully nowadays we have computers, so we have packages to do this work for us, this complete work for us. So we will directly get back those to the equations. So we will try to understand how these curves will come for the first order and second order equation, and then for a linear line and for a first and second order equation, and then the rest of the things will follow the same thing. So we will try to understand how we fit these curves, and that analysis, whatever we are doing for fitting the curve to the given data, is what we call it as regression analysis. Okay, so the non-linear relationships in the third figure, whatever we have seen here, is following a polynomial relationship of what form? It is forming a cubic polynomial equation, which is cubic order of a polynomial equation, which is ax cubed plus bx squared plus cx plus d. So it can also be treated as a linear regression. Suppose if we are taking x to be x1 to be x cubed, x squared to be x2, then you can write this in the form of a linear kind of an equation. ax1 plus bx1 plus cx plus d. That way also you can write and solve. For examples, so regression laws covered by linear regression model, how they can be. So if the regression law is y equal to ax plus b, the equation is in the form of ax plus b, it is a linear fit. Okay, how we can draw this? It will be a straight line on a linear graph sheet. It's not a logarithmic graph sheet. On a linear graph sheet, it will be a straight line with a particular slope. So that is basically depending on your slope value, your a, and then what is the intercept will be talked about by p. So based on that, you will define that straight line for the given data. Suppose if it is y equal to ax plus ax power b, so if the equation is set like this, then it is a power law fit. We say that we have fitted a curve which follows the power law. So we can say that it's taking an exponential power. So we also can draw this as a straight line on a linear graph sheet. So this also will be like a straight line, but it will be very steep, like an exponential thing. And then we also have y equal to ae power bx, which is an exponential fit. But it can be a straight line on a logarithmic graph. It appears to be a straight line, but on a linear graph sheet, it will be an exponential curve, either increasing or decaying curve. Okay, it can be anything like this on a linear curve. Let me show. It can be an exponential curve like this, or it can be any decreasing curve like this, whatever it is. It may be expanding like this or any other ways. Okay, so that will be the form of it in the ax, a or bx, depending on the order. It will vary how it will fit. And then we have the fourth one. We call it as the whatever we call it as the ax squared plus bx plus c form. That is in a polynomial fit may be there, which basically from one equation, this is ax squared plus bx, and then we will have. And then we can also derive, depending on the power will vary. So it's called a quadratic fit, we call it as, and this can be done by multiple linear regression. Okay, this can be solved by multiple linear regression. Okay, so now how do we do this linear regression? We are first starting with y equal to ax plus b linear regression form. How do we find out this kind of a data? So we have a given data set of n statistical units. So we have n number of values. Okay, So 1, 2, so on, n. Okay, this is serial number. This is n. Okay, and then we also have xi. This is the input values, and then for that corresponding we have yi. Okay, this is a set of data that we have. Okay, so now we want for this xi and for each yi, these are discrete in nature, and I want a continuous function in the form of y equivalent to ax plus b. Y equivalent to ax plus b. All right. So where b generally is the error term, we take this as to be error term. So this we will take it as the error term. So now for a best fit for this line to be, if we want to call that as a best fit, what can be the requirement? The requirement can be this a and b, the derivative with respect to a and the derivative with respect to b should be close to 0. So if there is a curve, where can we get the derivative to be 0? If there is an expression, suppose this is a function, where can be the values can be 0?
At maxima or minima, sir?
Correct, at here or here. So those lines will tell you that they are linear. So therefore, what we are trying to do is the minimization requires that dou s by dou a equal to 0 and dou s by dou b equal to 0. What is this as? This is nothing but your deviation expression. What is yi? Each yi from this expression. Okay, whatever the value from this. Now that will be from axi plus b. From where it will come? We have derived an expression y equivalent to axi plus b, yi equivalent. So whatever the each input, if I put it into the expression from the equation, I will get another yi from equation, right? From equation, regression analysis equation. So what I'm trying to do is I'm trying to find out this minus this, which is nothing but axi plus b, and I'm trying to figure out what is a, what is b. It can be any fit, but when can be the best fit will come? When the best fit will come? When the derivative of the standard deviation with respect to a and with respect to b is 0. Okay, so here we could see here that an equation is given, which is in the form of a linear line, y equivalent to ax plus b, kind of it, right? So you can see here y is there, x is there. We have data points. See now, no data point is on the line. If you are of the mindset that all the points has to be on the line, that's a wrong thing. But if you see the deviation from this point, this deviation, this is minimal. And you compare all of this, this line will be the minimal, and it is at a minimal distance from all the points. So that line I am taking it to be my equation of the line. So it's nothing like, it's like a average value line. That is what I am trying to find out. So that what it will do, it will kind of, when I solve the dou s by dou a, I will be getting 1 by n sigma y minus axi minus b minus xi, because a we are derivating that with respect to a, so therefore minus xi will come out. And similarly, when I solve with dou s by dou b, so dou s by dou b with respect to the derivative of standard deviation with b, for that expression will again give you minus b, that is minus 1, which is equivalent to 0. So now, I mean, we solve these two equations. For solving these two equations, we have rearranged these above two equations, which comes in the form of nb plus a into sigma xi equal to sigma yi. That is the summation of all the values of xi and yi. Similarly, the second equation will give us b into sigma xi plus a into sigma xi square is equal to sigma xi yi. So solving these two expressions, b for b and a, if we solve this expression, we will finally end up with a equivalent to n. N is the number of readings. Sigma xi yi. We have input, we have output. Xi into yi we will find out. The summation of all of that is your sigma xi value, minus individual summation of all the xi's, individual summation of all the yi's, all divided by n into, we will try to square the xi values and xi value whole square minus the summation of xi whole square. This is the summation of all the xi square values. This is the summation, the summation of xi whole square. Similarly, for b also, we will be getting this expression. So if at all somebody gives you xi and yi, okay, xi and yi, what you need to do, I will show you in the next slide. So just remember this expression. What you are going to do, you have given yi, you have given xi, you have to find out xi into yi and then xi square. Okay, yi, xi is given in the table, the proper equation, and you are asked to find out what is find the suitable good fit equation, linear equation for corresponding to this data, given data. So what we will do for a given yi and for a given xi, we will try to multiply that and we will write down 1.2 into 1, 1.2, 2 into 1.6, 3.2. And then you square this xi term, you have squared. And then sum all these yi's, sum all this xi, sum all this xi yi, sum all this xi square. Okay. So now for finding out a, what you need to do is how many, what is x, n here, 1, 2, 3, 4, 5. 5 into sigma xi yi, which is 44.76, minus sigma xi 15.2 into 12.6, divided by 5 into sigma xi square. So sigma xi square is 58.16, minus sigma xi whole square, that is 15.2 whole square. That will give you my a value. Similarly, following this b equation, we will get the b value. So therefore, your y equivalent to a, whatever a, you will get that value into xi plus this p value. So that will give you a good linear regression fit. Okay, this is how we solve the regression equation. You may ask, sir, what about polynomial regression? That means if it is not in a single linear relationship, if it is having polynomial kind of a relation, then how do you do that? If it is second order, third order, fourth order, then how do you do that? So if the order is kept on increasing, then the more and more complex equations you have to solve, more number of calculations you have to do. So if it is a quadratic equation, the second order equation, we will be finding out y equivalent to ax square plus bx plus c. Okay. So if the function is of this order, then you will write down y equivalent to x square plus bx plus c. So the deviation will be similar, same as earlier. This is yi minus ax plus b for linear. For this, it will be y minus axi square plus bxi plus c whole square. So now dou s by dou a should be equivalent to 0, dou s by dou b equal to 0, dou s by dou c should be equivalent to 0. And if you expand these terms, you will get 4 different expressions. Expanding and collecting terms, you will get 4 different expressions. And by solving that, you will find out, you will find out the values for, if you solve this expression, you will find the values for a, b, and c. If you solve this expression. Similarly, if it is a cubical equation, now a, b, c, d you have to find. Fourth order a, b, c, d, e you have to find. Likewise, you can write down these expressions and solve and you can use the polynomial regression fit. So this is how you are trying to find out the fit by using regression analysis. It may be least square method or any method by which you are trying to find out the fit for the given data. So now what you are trying to find out is the goodness of the fit given by a term called the correlation coefficient. Okay, so you have got a curve which is linear, and then you also draw for the same data, you also draw instead of a linear line, you have a quadratic equation. Which one is fitting better? How do you understand which one will be the best thing? So that may come many a time. So E is the given data and capital E underscore F is your data given by the equation, linear fit equation. And on what basis you can say that this fit is good? For that we are defining a term called R square, which is called the correlation coefficient. How it will be find out, I will tell you here. So the goodness of the fit, whatever the fit that we are creating, how good that fit is will be explained by a term called the correlation coefficient. So for that, total sum of squares we will use. Suppose if total sum of squares will give you, like, the total sum of squares is a variation of the values of dependent variable from the sample mean of the data, dependent variable, from the sample mean of the dependent variable. So therefore, that is basically your total sum square, correct? So is a variation of the values of dependent variable from the sample mean of the dependent. So yi is the individual, whatever from the expression, whatever we are getting, this is that yi, minus y bar is the mean of this value. The summation of these squares, we are calling it as total sum squares. Similarly, we also have regression sum squares, which is also known as the sum of square due to regression or explained sum of square. It tells you how well a regression model represents the model data. The regression sum of square, what it will tell you? It tells you that how well the regression model represents the data, measured data or modeled data. So what does that mean if it's a higher value? A higher regression sum of square indicates that the mode doesn't fit the data. Suppose if this value RSS is pretty higher, that means the deviation is pretty high. It has to be as low as possible. Okay, when it is very high, then that means you are having a lot of error. So this is what from the expression, regression sum of square is yxi minus y bar. Y bar is the mean from the data. Yxi is what? It is nothing but whatever value for I value, what is the value of yxi you are getting. So from the data, from the fit, whatever values you are getting as outputs, if you put those values minus the output square, then your regression sum of squares will be there. Okay, one is the individual data given yi minus the average. Another thing is from the model fit, whatever you are getting, that value plus this. So the total sum of squares is nothing but from the individual data. Regression sum of square is from the fit data. So the total residual sum of squares is nothing but it has to be the total the total of RSS plus RESS. RSS value is what? This regression sum of squares. Okay. So now what we are trying to do is residual sum of squares will help us to find out the when we add this residual sum of squares to the regression sum of squares, we will get the actual TSS. So now the difference between the observed data value yi and the predicted value, so that is in the residual or error that is coming from the yxi. So this value is for a given xi, so that means for input 1, you measured this experimentally to be 2, but the fit may give you 2.1. So that is nothing but, therefore, what you are trying to find out, RESS, is nothing but the summation of yi minus the fit value whole square. The summation of this whole deviation between the measured data or the discrete data minus the continuous data whole square. That is what we are trying to find out, which is nothing but your RESS. Okay, so this value is yi minus yixi whole square. So therefore, from these values, from these three things, it is defined that the coefficient of determination or R square. So coefficient of determination or R square is nothing but regression sum of squares, okay, which is nothing but this value, regression sum of square, which is nothing but this value, that is from the actual data to the data obtained from the expression, the square sum will give you the regression sum of squares, which is nothing but sigma I equivalent to 1 yxi minus y bar square by total sum of squares. What is total sum of squares? Total sum of squares is defined here. Okay, so this is total sum of squares, which is nothing but yi minus y whole square. Okay, so that will give you the regression sum of squares is basically yxi, that is from the model data, from the fit, whatever the y value that I obtained minus its mean whole square, the whole summation to the total sum of square is actual data minus its mean whole square sum. The ratio of these two will give you the R square. This makes sense or not? So this is your coefficient of determination. So that means what? R square value is what? If it is, for example, 1, that means if the value is 1, that means the actual data minus the individual actual data minus its average squared sum will be equivalent to the fit term minus this y bar square term. So that means the fit minus the average value, the squared sum, they both will become equal, correct? So that means what? It means whatever the data that I am finding, whatever the data that I've got, and the modeled fit is also giving the exact deviation, that means they are both one and the same. So your R square value should be close to 1. So that will be the best of the data. So the same thing, what I'm trying to do is I am trying to write down in another form, like 1 minus residual sum of squares by total sum of squares. 1 minus residual sum of squares. What do you mean by residual sum of squares? That I have defined here. Residual sum of squares is nothing but yi minus yxi whole square, the summation. Yi is the individual value of output for a given individual input, minus yxi, this is coming from the xi when incorporated into the expression or equation. The squared sum is nothing but the difference of these two is nothing but residual sum of squares. This is already defined. So this expression can be written as 1 minus of residual sum of squares by total sum of squares. Okay, which will give the same thing as this. Suppose if you write this expression yi minus y bar whole square minus of this, so yi will get cancelled. Again, it will be minus and minus is there, so this will become yxi. Again, this here it's minus y bar square, it will be the same, and divided by the same. So the same expression I am writing in another form, 1 minus yi minus yxi whole square summation divided by yi minus y bar whole square. So this will be nothing but your coefficient of determination. This value, when it is as close to 1, that much good for you to say. So the correlation coefficient is nothing but plus r minus square root of r square. Okay, so that will give you the correlation coefficient and coefficient of determination. Coefficient of determination means whatever the fit that you have got, you have to make sure that the data has to fit, whatever the fit the value it is giving, it should be giving you R square value to be close to 1, 0.97, 0.98, 0.99, like that. Suppose you have done an experiment, you want to publish that, you want to convey that good result to the world. So the data you have presented and you want to give the data in the form of an expression, and you fitted a curve, and how people will understand whether your fit is correct or not. How do they say that? So you have a linear curve, you have an exponential curve, which curve fits better? You look at the data and then you plot the curve, and wherever the R square value is minimal, that curve you will say that is the best curve. Okay, so it will be evaluated by the coefficient of determination. So this is what all about the analysis, and there is a lot other things also, but from the syllabus point of view, we are actually stopping at this point of time. So now let us see how the regression analysis can be done in the form of formulas. So we have x and y values given. Okay, from that you have to find out what is your correlation values. They are asking simply to fit a linear function y equivalent to ax plus b. Okay, y equivalent to ax plus b. Therefore, you need to find out what is a, what is b, and what is r, what is the regression coefficient. So you can see that what can be done. First, you need to find out sigma x, sigma y, xi into yi. First, multiply of these two, xi into yi, and then summate that sigma xi into yi, and then you square the xi term, xi square, and then summate that sigma into xi square. And now you know the formulas for a and b. Okay, that's what I have done here: yi, xi, yi, xi square, and then I have found out the summation of yi, xi, and then a sigma xi, yi, and then sigma xi squared value. The summation of this whole terms is 58. Now we will try to find out what are the number of values 1, 2, 3, 4, 5. N is 5. So therefore n into sigma xi yi 44.6 minus sigma xi that is 15.2 into sigma yi, the 12.6 divided by n into sigma xi square minus sigma xi whole square minus 15.2 whole square, which is 0.54. And similarly, b value we are also finding out from sigma yi into sigma xi square minus sigma xi yi into sigma xi divided by n into sigma xi square minus sigma xi whole square, which is giving 0.87. So we have found out a and b value, so that therefore the desired value equation is 0.540x plus 0.879. And then a plot of this relation we have to draw again. So we have drawn this plot with that expression, and this is the curve that you got. Okay, so always remember that based on the r square value, simply r square without actually drawing the data, you are not sure whether the fit is perfect or not. You have to write the equation, plot the equation, and then only you find out the r square. That is the correct way of doing it. Okay. And there is another problem. So you are expecting to have a quadratic relationship with this. So you are asked to find out what is a, b, x square plus bx plus c. So what is a, b, and c? You are asking to find out that value. So to do that particular part. Okay. So look at the textbook. It is like an experiment to you. So just go back and see what are the, how do you find out a, b, c, and solve that particular function, solve for particular equation, this equation. Now I will try to show you. Up to this, any questions you can ask me. Any questions related to this? Is it clear? Can I feel that your silence is saying that you have understood, even though I know that some questions may be there.
Yes, sir, we understood.
Fine. Then what we will do is now we will try to go on and see how this can be done on a Excel file very easily. Okay. Many of you may be knowing it. Is that many of you know this? Should I need to teach this, or you people know this particular thing? If you want to show me once, I'm ready to show. Quickly. Or everyone knows how to draw this in Excel?
Sir, we don't know.
Yeah. So now we have an Excel file in MS Office. I think you all know how to open the Excel file. Just right click it and then you have new, and then open the Microsoft Excel worksheet. If you have MS Office as a package in your system, you will be having this. Maybe one or two may not be knowing this. That's why I'm repeating. Don't feel that sir is telling these things also. If one person is not, it's also not there, I don't want him to be new to this particular thing. So this package will allow you to draw any pattern curve, any data that you give. It will kind of plot a curve for this. Okay. So you have different kind of things. So let us say you have x value here and you have y value here. Okay. So you have 1, 2. Likewise, you have data of some 6 or some 8 values, and I'm having a data like 20, 35, 35, and then 40, and then 42, and then some random data I'm just taking, 57, 60, 70, 90, some data I'm taking. Okay. Now, how to draw this data? Okay. Is it visible, right? Okay. This is visible. Yeah. Now, what we have to do is you have to select these two. Okay. Select these two, and then go to insert. Okay. I'm showing it again. Select, and on the top you have home, and then you have insert. And go to the insert. You are seeing some charts over here. So this data can be shown in many ways. This is a histogram. this each one will be different. See, for 1 you have what value, for 2 it's a 3D column, it's a single column, so it will tell you what are those values and all. See, y-axis what you are getting and x-axis what you are getting. Okay, so that way you can show, this way you can show. So there are different ways how you can plot this. You do need not worry, just only if you give the data, it will plot for you. So like bar diagrams kind of a thing is also there. Okay, and you also have this curves, 2D line curves, how it will be. Okay, and what is that? We can also have a pie chart kind of a thing. So each one how much percentage. So different things are there. Only thing is now we are going to insert scatter. Okay, I'm going to insert, and then in this I'm finding out scatter. In scatter, you can draw the x and y axis. Okay, so you have 0, 1, 2, 8 values, and the corresponding 20, 35. You can see here 2 is 35, somewhere in between we are having this. Likewise, you got the plot. Now, this is discrete values. Now, I want to find an expression for this. So now, plus, you can see here, chart elements. When you move your cursor over it, just click it on that. You got a plus, you got an edit, and then you got a filter. This is chart styles. You can style it in any way. That means colored schemes, whatever colored schemes you want to show like this, or you want to show like this. You can do whatever you want, but initial thing is you have axis. You want to put x-axis and y-axis. What is primary, horizontal, primary? You can do that. You can show that, and then axis titles you can give. What is x and what is y? You can give the titles. Chart title, what you want to store here, that can also be changed. Data labels, what are the values with the actual data you can show. Error bars, how much it is deviating from the mean value you can show. And then grid lines is different, that it shows the lines over here. The intermediate lines it will be showing. Legend is different. This what is the series, number of data is there, then it will help us this related to what data. Suppose if you have Z, again some data is there. So I can plot to two things on one particular thing. Okay, let us say 40, 70, just plotting something. So what I'm trying to here is x is my x-axis, and then y I can draw, and similarly z also I can plot in the same lines. So that I can do. So that when I plot like that, legend will help us to determine which series is it y or is it related to z. That will help by legend. And then the important thing is your trend line. You can see here. Okay, you got a trend line here. When you put this trend line, you have so many options, right? You have linear, you have exponential curve, linear forecast, 2-period moving average, and if you go, you will more options you can see over here. How you want to have linear is the simplest way. Okay, linear is the simplest way. But as I told you, how good this chart is. Okay, so you want this expression. What is A value and what is B value? For that, you need to give display equation on chart. This equation, A value is 8.8095 and B is 12.107. These two values are calculated from sigma, whatever we find, n into sigma xy minus sigma xi into sigma yi by that expression will deal these two. So already they have written the code. That's why you are getting directly this A value and B. Okay. So now you got an expression. Fine. Now what is supposed to be is you have to see what is the R square value, how much it is, 0.9549. Okay, so whether this is good enough, what R square value, how it should be as close to 1 as possible. Correct. So let us see whether any other thing will help us. Now, trend line. Now you can see here, suppose if I put an exponential, take out linear, this value linear, I'm taking it out, delete. And if I have this exponential term, for example, this exponential term, and an exponential term will have, if you want your equation, sorry, it's exponential value, display equation, you can see a e power bx. A is 20.629 e power bx. Now you can see here there is a trend line. Now you get the doubt, which one is better? That can be taught by this. So now what is R square value? It's 0.935. Now which one is better now according to you, linear or exponential?
Linear, sir.
Yeah, that's how you will define. Suppose if it is logarithmic, okay, so R square value is how much? 0.85, which is even, that means the deviation is getting increased. It is not actually replicating it. A polynomial. Now this can be a good ploy. Now you have polynomials. I'm taking this 2 out. Polynomial, if I take, if it is ordered 1, already it is linear. Therefore, it is ordered 2, from 2 onwards, it will start. Now you see, if it is R square is 2, then your R square value is how much? 0.96. Okay. Suppose if I increased it, R cube, if, that means it becomes cube. Okay. So now I changed it to cube value. So that means polynomial of cubic order. See now how much it is? How much?
0.9848.
So that means the cubical thing. So why the cubic is having more points? You can see over here, I'm taking the second order polynomial equation out. Now you see, most of the points are on the line when compared only this and this, but the deviation is also pretty low. So that's why you have 0.9848 curve. Let us move, and you may think that, sir, if you give 4 order of point, whether this will give you better or not. Okay, let us look at that. Fourth order, it's not much change. So you can see here, suppose if I give 5, now ordered 5 expression is much better. See, what is the value of this one? 0.9932. So this is 0.9932, but the order of the expression is this one. Now this expression I will convey or communicate to the world that this is the equation that I have to use for this data to be, for any intermediate data to get accurate prediction, I will use this particular expression. Okay, now the COVID thing has happened recently, and you might have heard that some Kanpur or Kanpur IIT professor has predicted it, and it happened exactly the same way. Same thing. They have taken data, lot of data from somewhere, predicted and formed a curve like this. They have this peak values with respect to time, and from that they found out an equation, and they said that okay, this is the region where they are getting. I hope this is useful to you. This will not be asked in the exam. This I taught you just to make sure that you learn this Excel as a good plotting software. Okay. Any doubts in this plotting software? Or it's fine, right? It is easy. So the mathematics behind finding this A, B, C coefficients or the exponential coefficients and all is the regression.